Hello and welcome to my presentation about the Wiener process. This is going to be a fairly introductory presentation where we're going to be going over some motivations and some more intuitive ideas about it and not necessarily have full mathematical rigor. So to begin with, we'll be going over the properties of a random walk and more of an intuitive sense behind a random walk. And then we'll be going over the Wiener process, properties of the Wiener process, some visualizations of it to make it easier to understand, and variations of the Wiener process. And then afterwards, we'll be lightly discussing applications of the Wiener process in physics, finance, and other applications. So let's begin with random walks. So a random walk has three main properties. It is stochastic, and it being stochastic means it's random. Has an expected value of 0, so if we have a random walk rt, then its expected value at time t is going to be 0. This does not mean it's going to have a value of 0, it's just on average it will be 0. And its standard deviation is proportional to the square root of t, which also means the variance of our random walk, rt, will be proportional to t. Again, this is just a general trait about random walks. This isn't going to say anything about any particular singular random walk in general. So, a very elementary random walk that we're going to be discussing is going to be a simple game. So, imagine we have a coin and we flip it. Our value starts at 0. If we flip it and it comes up heads, we get 1 point. If it comes up tails, we lose 1 point. So the pictures I'll be showing are going to be simulations of 1,000 games where we have 1,000 coins, we flip them, and we record how many points we get. And this is going to be after a certain amount of flips. So after 0 flips, no flips have been done, we're all going to have the same amount of points. It's all going to be 0 points. If we do 1 flip, some will come up heads, some will come up tails. On average, it'll be 50-50. In these simulations, slightly more came up tails than they did heads, but it's kind of around 50-50. Now if we do 2 flips. So 2 flips, if we do that, we're going to expect that around half of the ones that came up heads are going to come up heads. Half of them are going to come up tails. So the ones that come up heads are going to move to 2. The ones that come up tails are going to go to 0, because 1 plus 1 is 2, 1 minus 1 is 0. And similarly, for the ones that came up tails, the ones at -1, roughly half of them are going to move up 1, and roughly half of them are going to move down 1. So let's see if that holds. And there we go. We can see that the middle stack of the zeros is roughly twice as big as the 2 outside stacks, and it roughly contains half of all of the flips. This is exactly what we would expect, and these two roughly contain 1/4 of all coins. And because you're equally likely to get heads or tails, the expected value of any singular flip is going to be, of course, 0. So what if we're here and we flip it again? What do you think that's going to look like? Yep, you're going to move some up, some down. And they'll be on 3, -1, 1, and 3. So you can see this distinctive shape starting to form, which is also important for random walks. And we'll see it a little bit more clearly soon. But if we keep doing this, what if we go to 5 flips? We're going to see this shape, which, again, the shape that it's forming is a little bit more distinctive, right? Okay, what if we go to 10 flips? 10 flips, we have a big peak at 0, which contains, it looks like slightly more than a quarter of all flips. And then -2 and 2 contain roughly a fifth. And I just go down from there. And there's sharp increase and the sharp decrease. Okay, what if we go to 100 flips? Remember, we only have 1,000 simulation runs here in total. So what do you think 1,000 flips is going to look like? Sorry, 100 flips is going to look like. 100 flips, it's going to be a lot more chaotic. You can see that between this and this, there's a steep jump between. It looks like -2 and 0. Between -2 and 0. We have one down here at -32. We have one all the way up here at 40. We can see that it would be possible for there to be some at 100 if they just got all 100 all heads every single flip for that coin, or -100, but the furthest we have from 0 seems to be 40, which means that they got it, more heads than tails a significant portion of the time, but not exclusively heads. Also, something to keep an eye out is, notice on every single one of these, whatever step count we're on has the same modularity to 2, so as where all of the coins are on. So step 5 is odd, and all of the coins are on odd numbers. Step 10 is even, all of the coins are on even numbers. Similarly with step 100, all of the coins are going to be on even numbers. So it's going to be random. The expected value is 0. Standard deviation is the square root of t. We can see that here as the distinctive shape mentioned earlier is a bell curve, which is what this looks like. That is a horrible bell curve, but random walks are going to form this bell curve shape after many, many simulations. In this case, the variance is going to be exactly the number of flips. So in this case, the variance is exactly 100, and the standard deviation is going to be exactly 10. Another thing that is important about random walks is at low dimensionalities, they have a property called Gambler's Ruin, which is low-dimensional walks will eventually come back to the origin, which is 1 or 2 dimensional random walks, which is a concept I'll get into soon, will eventually go back to the origin regardless of how far they stray or come back. So any single simulation of this we can see as a random walk. So this one flip that went all the way out to 40 is a single random walk all the way there and back. Any one simulation is a random walk. This is an aggregate of 1,000 random walks. Now, let's get into the Wiener process. Now that we've discussed random walks, what happens when we reduce the step size in a random walk? So, we were just discussing random walks, and we had discrete steps. Step 1, step 2, and we were discussing this as flips. So what if we had a step 1.5? Step 1.5. What if we had a step pi? What if we just reduce the step size so as a limiting process so that the amount of time that each step took went to 0? Well, that would turn this discrete random walk into a significantly less discrete system called a Wiener process. And because we're generating this from a random walk, there's going to be a lot of similarities and properties to the random walks. Namely that the Wiener process is stochastic, has an expected value of 0, and a standard deviation proportional to t, the same as the random walks. So we have expected value of the Wiener process, which we'll describe as w of t is 0, and the standard deviation of the Wiener process is going to be the square root of t. And again, this will imply that the variance of the Wiener process is t. And for future's sake, I'm saying w of t is a single Wiener process. So the expected value of any single process is going to be 0 at time t. The standard deviation is going to be proportional to the square root of t, and the variance is going to be proportional to t. The big difference between a random walk and the Wiener process is that the Wiener process is continuous, meaning that the definition is continuous. Basically, is complicated, but an intuitive way to think about it is you can trace it without picking up your pencil as you do it, or for any point you can draw there's no circle that you can draw of any size that doesn't include more points of it. Those are two good ways to think about continuity, which the Wiener process satisfies. So I'm going to erase all of this, and we will give you some visual intuition to what the Wiener process will look like. So here's a single Wiener process run. You can see that after 10,000 units, out of 1,000 units of time, it goes up a little bit, and it goes down, and then it goes back down, and back up. So we can see that even though it has expected value of 0, it is of course not 0 at every point. It is, and additionally, because it is stochastic, it is completely random in whichever direction it moves, and because it's stochastic and continuous, the value that it moves by is also random. And just to show you that not all Wiener processes are the same, here is 5 Wiener processes, all starting at 0, each a single simulation of a Wiener process up to 1,000 units. You can see here that the blue one starts out much higher than all of the rest. The green and orange one kind of go down a little bit. The orange one does a negative, but every single other one ends positive. The red and blue are both significantly positive. And it looks like the purple and green ones end up, after 1,000 units, about at 0. I don't think it's exactly 0, but it's approximately 0. So here we can see a lot of variation between the same fundamental Wiener processes. These are all the same simulation. There's no setup differences between these, but because it's a stochastic process, the results of it is, of course, random. And each individual time is random. Even though, again, it's continuous, there's no jumps, it's just random in how it moves through time. Okay? So, now that we have a idea of not only the properties of the Wiener process, which are very similar to the properties of a random walk that we established earlier, we also have a visual intuition for what a Wiener process could look like. We can discuss some variations of the Wiener process. So here's the Wiener process with drift. If we let W of t be a Wiener process at time t, so we have W of t, and we'll say that W of td, so W of dt, then how are these going to be related to each other? What does it mean to have drift? So what it means to have drift is that the expected value of the Wiener process is not going to be 0. It's going to be something proportional to time. So if we look here, then we can describe this one as W of td, the Wiener process with drift, is equal to a single Wiener process plus d times t. So at time t, it will have drift d times t. So say at time 1, if we have, say, d equals 1 and t equals 1, then it'll be 1 more than a single Wiener process, than this Wiener process on average. This also means that if we were to take the expected value of this, it's going to be equal to the expected value of a Wiener process plus the expected value of dt. The expected value of the Wiener process is 0, and this is not stochastic at all. So this is just going to be dt. So now we know that the expected value of a Wiener process with drift is going to be equal to time times its drift. Additionally, because that's not stochastic, we can do the same thing with the variance, which won't be such a nice calculation, but the variance is going to be similar to the variance of sorry, that's not expected, that's a variance. Variance is going to be similar to that of a normal Wiener process. And I will highlight, we will shortly see a way of thinking about the differences in a moment. So here's an image depicting two different Wiener processes. This is from time 0 to 2. The red one is a normal Wiener process, and the blue one is the same Wiener process, so the same values at all the same points, except for it has drift of 1. So we can describe this as W1t equals W of t plus t. And we can see at time 1, there's about a 1 unit distance between these, and at time 2, it's about a 2 unit distance between these. And it'll grow like that as it continues. So it's drifting upwards, is why it's called a Wiener process with drift. Now, let's discuss a two-dimensional Wiener process. Here's an image of a two-dimensional Wiener process. It is just two Wiener processes, one for each dimension of movement. You can see how it's not like just right angles of movement. Here's a very good place to see that. It's not just right angles, it's just two Wiener processes moving in different dimensions. And we can, of course, generalize this to be an n-dimensional Wiener process. If we let W of t be a singular Wiener process at time t, then W n of t will be an n-dimensional Wiener process. And of course, these Wiener processes, these individual Wiener processes, don't have to be normal Wiener processes. They can also be Wiener processes with drift. I don't have an image for that, but it will be similar to the two-dimensional image here, except for one of the Wiener processes would drift away from what its normal value would be. Now let's get to some applications of the Wiener process. The Wiener process can be applied to physics, which is one of the initial motivators in researching it. Brownian motion, the random movement of particles in the air, is so closely connected to the Wiener process that they're usually interchangeably named. Quantum mechanics, they're important for path intervals in quantum mechanics, because quantum mechanics has its own special machinery. And also diffusion, which is closely related to Brownian motion. Within finance, it's often used in option pricing and stock movement. Wiener processes and Brownian motion in general is often used to simulate stock movement. And in other fields, in biology, it can be used for modeling evolution. In mathematics, it can be used for stochastic calculus. It's a core part of stochastic calculus and Ito calculus. And electrical engineering, it can be used to simulate noise, along with other applications. So, to round it all up, we began this by discussing properties of a random walk, and then discussed how the Wiener process is related to a random walk and how its properties are related to that of a random walk, along with visuals and brief descriptions of variations of Wiener processes. And then we lightly discussed some applications to other sciences and other fields of the Wiener process. Thank you for coming, and thank you for watching. Have a nice day.